You are descending through 2,000 feet into Delhi's Indira Gandhi International Airport. The cockpit windows reveal absolutely nothing but a dense, zero-visibility gray wall of fog. At this point, your optical sight is useless. The only things keeping this aircraft from hitting the ground short of the runway are invisible radio waves, specifically the instrument landing system, radar, and area navigation. Understanding how these systems calculate position, speed, and descent rates is how pilots survive in the air. It is also how you pass the most calculation-heavy section of the DGCA Commercial Pilot License Air Navigation Exam. This diagram shows the geometry of an instrument landing system. The ILS creates a strict three-dimensional funnel down to the runway. It uses a VHF localizer to provide lateral left and right guidance, and a UHF glide slope to establish a vertical descent path. While the ILS guides you down, radar acts as your eyes. Primary radar bounces raw energy off targets, while secondary surveillance radar talks directly to aircraft transponders. But the trap for the exam is the airborne weather radar. Heavy rain cells block the radar waves completely, creating a blind shadow area behind the storm where other severe weather can hide undetected. To navigate between airports, we rely on RNAV. Instead of flying zigzag paths from one physical ground radio station to the next, RNAV uses satellite and ground data to compute smooth, direct, algorithm-driven flight paths. This RNAV system is managed by the Flight Management System, which draws from two distinct databases. The navigation database stores route geometry, like waypoints and airways. The performance database holds the aircraft's aerodynamic limits, thrust configurations, and fuel flow data. Flying an airliner requires synthesizing these ground-based ILS funnels, radar echoes, and space-based databases into a single, cohesive picture of where the aircraft is. This formula calculates your rate of descent on a standard 3-degree glide path. The math is straightforward. Your descent rate in feet per minute equals your ground speed in knots multiplied by 5. Consider a sudden wind shear scenario on short final. If your aircraft encounters a sharp increase in headwind, your true airspeed remains constant, but your ground speed drops immediately. A human instinct might be to point the nose down to chase the runway, but the math dictates the opposite. Because ground speed has dropped, that ground speed times 5 formula yields a smaller number. You must lower your rate of descent to stay on the glide path. If you maintain the old descent rate at this new, slower forward speed, you will sink dangerously below the beam. Wind strictly dictates your speed over the ground, and that speed strictly dictates how fast you need to descend. This diagram illustrates the radar horizon. Because radio waves curve slightly as they travel through the atmosphere, radar can see just over the curvature of the Earth. To find the maximum detection range, you calculate the horizon from the radar antenna's height and add it to the horizon from the target aircraft's height. Let's test this with an ATC radar positioned at 10,000 feet, tracking an aircraft flying at 10,000 feet. You take 1.23, multiply it by the square root of the radar's 10,000 feet, and get 123 nautical miles. You do the exact same calculation for the aircraft's 10,000 feet, getting another 123 miles. Add them together, and the total radar detection range is 246 nautical miles. Calculating the ATC radar's range, but forgetting to calculate and add the target aircraft's horizon is the single most common mathematical error that costs students marks in this module. This image shows standard course deviation indicators. You fly toward the deflected needles to reach the centerline. However, a back-course approach flips the geometry. Reading a standard CDI inbound from the back gives reverse sensing. If the needle swings left, the true course is right. For India's Gagan system, memorize these counts: 15 reference stations, 2 master control centers, and 3 land uplink stations. For GPS RIME, you need 5 visible satellites to achieve fault detection. To isolate a faulty satellite, you need 6 for fault detection and exclusion. Passing radio navigation requires you to hold 2 distinct skill sets in your head at once. You must visualize complex spatial geometry for instrument approaches, while perfectly recalling rigid infrastructure numbers. Lock it in. Localizer is VHF. Glide slope is UHF. Ground speed dictates rate of descent. Radar horizon combines antenna and target ranges. The FMS separates navigation and performance databases. RIME requires 5 satellites for fault detection and 6 for exclusion. You have the theory. Now you need the repetition. Head over to clouddeck.in right now and run these scenarios in a timed mock exam.